Alright, sweet. So, we're here today. Is this YouTube? This is YouTube, right? YouTube, yeah. I was streaming earlier on Twitch. So, welcome and hello. Today, what I intend to do is solve this problem. So I left off on this problem last night, and I was stuck. I was quite stuck. A few things to note. I intend to so I figured out a solution. Or what seems to be a solution. So we'll try to solve this now. Start the clock. Try to spend a couple hours here. Try to solve this now, and excuse me. Oh boy. Oh. What am I even doing here? Yeah, so what I'm looking to do is to try to solve this problem now, and then see about the other problems that are on the site, and try to solve as many as I can in, I guess in a few hours or so, whatever it is, period of time. Yeah, I'll do it that way. I have an idea how I can solve this. I have an idea. So let's try it. I'll explain what I did after it if it works. If it works. Oh no. Misclicked. Oh, you're kidding. What? Alright, well, there goes my dreams. Hopes and dreams are out the window. Nice. You're kidding, right? You gotta be kidding me. Let's get some print statements in here. Hallelujah, 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 hallelujah. So this is the problem. Shucks. I thought you could just create a sequence out of Java long. What? You gotta be kidding me. This causes a problem? This is what causes the problem? Oh man. Shucks. Shucks. Jeez. You're kidding. If you try... What? What? Oh, that doesn't make any sense. Oh! No, it's fine. That makes sense. I get it now. That's okay. Range is... Okay, I think I understand. So you pick a random integer between, I guess 0 and 20 or 1 and 20, and that creates a range of integers. Okay, no, that's fine. That makes sense. But you can't fit this into a map, huh? Oh, I see what the problem is. I know what the issue is. I know exactly what the issue is. Aha. Oh, maybe not. Right. Hallelujah. 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 legal argument exception. A legal argument exception. How? How though? I think I know what the problem is. I think I know what the problem is. Do 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 Ah, that's what we need. Okay. Could be an array map as well, so I've got to handle that case too. Oh, I see. Could also be an array map. False. Huzzah! Hey! There we go. Give you false every time. Alright, that's probably good enough. So, sweet. So I'll explain what I did. Hallelujah, 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 hallelujah. Oh, come on, really? You're kidding. This works, but no, this doesn't. Oh boy. Jeez. Okay. Right. I think you gotta turn this into a sequence, these things. Oh my goodness. That's very funny. About that. So A1, B2. Okay. A1, B2. Hallelujah. Hallelujah. Oh, what? False? Wait a minute. What? Excuse me. You're kidding. Wait, what? Illegal argument exception. Huh? What? I'm not getting that here. That's confusing. Why wouldn't that... what? That's just extremely confusing. What is going on? Oh. Come on, man. What is happening? What is happening? Jeez. Jeez. Also this. Don't need that in there. Should remove that. Right. Huh. So what are we doing here? We want to... This actually seems to work in a local context. This returns false. Now, that's not true. Oh, that's what's going on. Okay, I understand what's happening. I get it. I was so confused why... No. It shows false. I see the problem. It shows false, but the issue is not that it's because it's false. The issue is that it shows false and then it performs the other checks, and these other checks fail because it is actually a map, and that's where you get this argument exception. That's why we're getting this as an exception, whereas this just gives you false. Right. Okay, got it. That's not. No, I got it. That makes sense now. The problem though is why isn't it returning true? Should return true for this. Like what is this? You know? What is this? Hallelujah. 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 So I think the issue is that if you take this as it is, right? This, I think this gets converted to a sequence here, right? Like if you say, so obviously, right, you end up with these two vectors, a hash map of one vector to the other. If you take this as a sequence, I think you get the same result. If we do that, yeah. So what if we flatten it first? Oh, of course. What? I guess not. I guess not. Okay. Right. So maybe we flatten the sequence. Oh boy. This is great. There we go. That's what we're looking for. Okay. Confusing as that may be. It's like, okay. Well, I don't know anymore, man. I think this will just pass the test cases, I guess. I really don't know. I really don't know. Hallelujah. 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 True. Got there. We got there. All right. Let's see how we do here. Oh, you gotta be kidding me. You failed the unit test. Nice. Excuse me? What? What do you mean? What is this? Oh, is map, that's why. How did that happen? Map. Excuse me. Excuse me. Oh my goodness. Vector. Vector. There we go. Alright. Minimum viable product. We did it. We got there. We solved it for the test cases and the test cases alone. You gotta be kidding me! Yeah, that's pretty bad. It's pretty bad. Let's look at the solutions. Cry about how we didn't come anywhere close to something simple. I mean, it's kind of simple, but it's pretty messy, I guess, at the same time. I don't know. I mean, it's kind of hard to make this not messy, though, at the same time. Read the solutions, and then, what are we doing after this? Read the solutions, and then after this, we are going to do what? I guess just go on to the next problem. Yeah, that's it. All right, let's go. Also, what is this? Oh, no. That's okay, I understand. Got it. Alright. What? Are you kidding me? What? Talk about succinct. Holy, what am I looking at? Wow. Alright, hold on that one. Whoa. Oh, you can turn it into a string? Oh, I didn't even think of that. Oh, that's clever. Oh, wow. Could have turned the object into a string and then check if the character's in the string. Wow, that's clever. I like that too. What else we got here? If you merge it with itself and it's equal to itself, that means to map. If you extended be conjoined with first and seconds, if extended is equal to extended into extended, then it's a set. Oh, I see. Yeah, I used that. And then if first of extended is equal to second, then it's a list, otherwise it's a vector. Kind of like Condell's. Maybe I should use that more. That seems a little more, a little cleaner than what I did. Because I did these that were very similar. So this is way more concise than what I have. This map, if it's even, and this isn't particularly good. I think the merge it into itself is the right way to do it. I didn't think of that. That's a good idea. Also, and then checking if it's a set. So he actually extended the set first, and then did some comparisons. So first to check if it's a set, when you extend the set, if you push the extended values into itself, if it's equal, so it could have been whatever, it didn't really matter what the extended is, it could have just been the initial set as well. When you push the initial set into itself, if it's still a set, meaning all of these things are unique, then it's still a set. Anything else, a vector or a list would make, this would be large, this would be not the same, it'd be larger. So into works. That's interesting. That's a little more clever, I think, more succinct. And then this is just, the same piece of code I had here, which is vector or list. Wow. Imagine that. Imagine that. Yeah, I guess so. Okay. Yeah, so I could have definitely done this a lot cleaner. Reversible vector. So what does cond do? Learn what that does. Cond. Set of test expression pairs evaluates each test one at a time. If the test returns logically true, cond evaluates returns the value of the corresponding expression. Doesn't evaluate the other tests. Cond returns nil. So this is a lot like a switch statement. It's basically a switch statement. Interesting. Oh wow, look at this. Reduce. What? What the heck is this? First glance doesn't look right, but apparently it's correct. Reduce with this function. Starting with this empty collection. Oh, I guess empty this, whatever this. Oh, I see. Oh, that's interesting. Oh. Huh. Wow. So, I think what's happening, also this could have been made a lot more efficient, but this doesn't matter that much. So I think what's happening is you convert, no, not much more efficient. Wait. What is going on? First and second. First is this empty collection. These other, right? It's first. Second is the value here, so it's an integer. And you're taking vector increment. What? Okay, I think the point is, okay, I think I understand. So it's a vector of two elements, which are going to be, you're going to go from 0 to 9, and you're going to have whatever the value is, range x over from 0 to 9, and you're going to have x and x plus 1 as a vector of two elements, and you're going to push that vector into the empty collection. And the reason you want to use two elements in your vectors rather than just pushing this range of 10 in there is because you may have a hash map which requires key value pairs to conjoin properly. So that's why you need two values. That's why it's a vector of two things. And yeah, and you just you empty the collection that you're given and use that as a basis and push all these values into that collection. And then you also repeat the same procedure for the four other vectors, four other possibilities, and then you just check against each one if what you started with and pushed into gives you the same result as of the others. And that's a pretty clever way to do it as well. I like that. That's pretty crisp, pretty clean approach. A fairly clean approach. I like that. And what else have we got? Foo, collection, empty collection. This vector is map is set. Condition. It's vector collection, vector map set. Else list. Hallelujah. 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 So quite a few people had some interesting solutions I liked. Solutions that don't like as much. GenSim. Don't know what generate symbol. Right. Interesting. If you can join sim with sim, and they contain. That's a map. Take X and place sim. If it contains sim, then it's a map. Oh, that's interesting. Yeah, you have to use symbols because if you use integers, it won't make any sense. If you use strings, you can maybe use strings too, but you could potentially have no, you could have a string in a set, but the symbols are unique, so you know it's not. Oh, that's kind of clever too. And then this is a very interesting question. My solution was terrible. My solution was incredibly unimaginative. Okay. So filter symbol equals this percent conj count equals 1 set. What does that do? Oh, I see. So oh, okay, I understand. So if you push the symbol in there twice and then you filter for only that symbol, if you only have one, then you know this is a set. And then finally, then you can check with the list or a vector depending on when you push one symbol and the other symbol, which one you get. Wow, so use cond. So I probably should have used cond in here. Like I could improve my code with, you know, all these if-else statements here. Did not need that, could just do cond like so. Yeah, well, hold on a second. Yeah, hold on a second. Okay, so all right. To return to what I was doing, what we were doing. We want to. Right. Yeah, you can use cond here instead. And what you do is here you can do else. All right, let's see. Sorry. Okay. All right. So what we want to do, right? So this would work too, and that greatly simplifies the structure of what we're looking at. And we also, yeah, and actually in this instance we can just replace each of these directly with what's here, and that would make it a lot cleaner as well. Cond is set of test expression pairs, evaluates each test one at a time. If the test returns true, returns the value of the corresponding expression, and doesn't evaluate any of the other test expressions. So there's something here, this else, that doesn't say anything about it. Returns the value of the corresponding expression and doesn't evaluate any of the other tests or expressions. Cond returns nil. Okay. So this else notes add a comment doctrine the final usage of else 9 years ago. Holy smokes. Holy smokes, man. Else is not special, any keyword will do. Oh, interesting. Okay. Non-null true will work. I've already used default. Else applies truthiness evaluation. Oh, it's a default value. Oh, I see. Otherwise, you can do any. Oh, that works too. I see. That's very interesting. Oh, no, I didn't mean to do that. How do you undo that? How do you... Let's see, does it still work correctly? I want to define this. Okay. Now we can call it map. Huh. Works. Sweet. Right, so that's what I should have done initially. Okay, so I guess it's not that much more. It's just making better use of the constructs here. Maybe though one of these cases does make a little more sense, which is this one. This is map portion. We can use, instead of is map, we can use merge with column. So if you do if equals collection, if you do collection, collection with merge collection, right, return the same thing. That will give you, I think, even better. Yeah, it's pretty concise. That's pretty good. It's pretty good. Let's try again here. Wow, look at that. That's not bad at all. Way more concise. Way more concise using this condition expression and also the merge instead. Yeah, that's pretty good. It's pretty good. This is pretty good too. You should take a look at that. It's even more concise. So, what does this do? Okay, so this says looks like you create a map, right? And you say, okay, if you empty the collection, then a map will give you map, a set will give you set, right? Okay. And then you've got, if this is reversible, and this could be nil, I suppose. So there's a few things going on here that are pretty clever, that are like kind of worth pointing out, worth talking about. This first thing, right? You empty the collection, whatever it is. If it's a hash, if it's a map, then we'll return a map. If it's an empty set, if it's a set, then we'll return a set. If it's empty map, return map. Empty set, return set. Okay, that's pretty clever. Now, the problem though is that this might return nil, this expression, right? If this returns nil, I guess the way Clojure executes is it executes in sequence, right? So, like if you do, how about this? How about this? Oh, no. Oops. Now this is a tricky thing here. So this works. Like this function is fine. This is okay. So this function is okay. This function is fine, but I don't really understand. Like if I do vector list. Why does this work? I guess is my question, because I understand this is a map and you're calling it with this value, right? But if it returns nil, why would you end up executing this, returning this? That doesn't make a lot of sense to me. Oh, that's why. Oh, I understand why. Oh, there's a lot of things going on here. Okay, it's pretty cool. It's actually pretty nifty, the solution. What's happening is this is a get. So you could alternatively just say, default, right? Suppose you did this, right? You get default. There you go. That's what it does. That's not an if else. That's a default value. That's if right. You can I forgot about that. Right. So when you call a get on the hash map, if you don't get what you're looking for, then you can execute actually another form here, which is the default, which in this case is an if statement. Now this if, on the other hand, what this does is says if it's reversible, then it's a vector. If it's not reversible, then it's a list. So it's not a map, it's not a set, it could be a vector, it could be a list. Apparently vectors are reversible, lists are not reversible. I didn't know that. What does that mean? I'm not even aware of that. So there's just a differentiating property between vectors and sequences if they implement reversible, which if you look at the Clojure, so I bet you if I went ahead and looked a little bit deeper at the two classes, I would see that there is an interface that's common to one class but not common to the other, and that would have resolved. Wow, that's amazing. So that's pretty clever. That is pretty clever, this whole shindig. Wow, really impressed by that. Well done. Yeah, I didn't come anywhere close to that. I didn't come anywhere close to something like that. Inspect the classes, find out whether or not find some difference between these two, vector and list. Arbitrary difference, reversible happens to be one of them. And then this is really clever too, that you can empty the collection and just check it against set or. Now I'm kind of surprised that emptying didn't, like, I guess, like here's another possibility. Like, why didn't he just do this? Something like this. Like, why even bother with this default value and looking up that property of duplicate key? Really? And bother looking up that difference between the two, that property. Oh, interesting. So it doesn't work for whatever reason. Not obvious to me at all why that wouldn't work. So I'm assuming there is a good reason that he had to do it a different way, but not clear at all to me why. Huh. Illegal argument type. Duplicate key. What does that mean? Why? Why would there be... Duplicate key. A little confused here. Okay, what does that mean though? Like, why would you get duplicate key, illegal argument, map? How does that happen? Why does that happen? Checking for duplicates. No. Like, what does it mean, duplicate key? Like, how does that work? What is that? I don't understand. Hallelujah. 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 So I don't know. I don't know why this creates a duplicate key, but that's part of one of the solutions is to check if it's reversible or not. You just check some property of what it implements, the class implements. That's pretty cool. It's pretty clever. It's pretty clever. Did not even come close to thinking about that. Wow. Okay. Yeah, I don't really know why this would give me a duplicate key though. That doesn't make a lot of sense to me. I don't know what that means. I don't know what's going on here. I think I'd have to like look a little deeper into the core, like I guess the source, to find out why this is happening. Why is this happening? So I think the issue is that both of these implement something, extend something that this map is considering to be the same key. And even though you can define this, when you actually try to execute it, you get this illegal argument exception, which I think because you didn't actually generate this map yet until you actually execute the function. It's kind of confusing, but I think that's the problem. And so it says this duplicate key, and it spits out, I guess, the interface that's shared, or the shared base class. Don't fully understand, but I think it's something like that. Or maybe it just prints out this one, which seems to be a duplicate of that one, the first one that's a duplicate. Like if I reverse the order of these two, I bet you it'll spit out the other one. Maybe. I wonder. Oh, there you go. Hey, you got the right idea. Yeah, they must share a base class. That's probably the issue. I bet you if I looked, I'd find that. So, okay, then that means, you just go ahead and use the reversible check, which looks like the following. Or actually, just you just do this exactly this. Wow, that's so good. That's very clean, super clean solution. Impressed. I am impressed. The other ones are just variations of these things, I think. Alright, so cond is good. That's something mental note. You can use cond. It's quite good. It's effectively a switch statement. And then the other thing is, right, you can use, I could have used properties. I can't, right, I can't put a list and a vector, empty list, empty vector as keys into a hash map. That'll cause a problem, probably because there's some base class that's shared between those two. An empty vector and empty list as keys to a hash map causes an error. Something that I learned as well. So cond we learned about, that we learned about, and then we also learned that I could have used, which is a little less useful, but I could have used a proper, could have used implementing interfaces to differentiate between these base classes, because they don't all have the same interfaces that they implement, and each of those interfaces have reversible, associative. Excuse me. They have checks you can use, built-in checks, so to figure out to differentiate. So that's kind of interesting. All right. That kind of goes with like not inspecting the class, but not exactly. I mean, it is and it isn't, right? I mean, you can inspect the interfaces that the class implements rather than inspect the class itself. So, yeah, okay, anyway. All right, moving on. Let's go to the next one. Learned a bunch of stuff there. That's cool. That's good. I feel like I don't get nearly as many folks over here on the streams than I do when I'm over at Twitch, which I guess is good and bad. I'm not sure if that matters. I kind of would prefer to do things on YouTube because it's got a larger viewer base, something like that. It's good, like you get a lot more exposure. I guess. I don't really know. I don't know. Now I'm conflicted again because I was kind of half expecting some people to be interested in these videos, but it's like, who knows? Whatever. I'm not gonna. I think. Anyway. Okay. Let me just continue. We'll just continue. We can ponder later, what to do about not really pulling a lot of people to watch. I don't know if that matters. Like, I don't know if I should even be thinking about that, actually. Well, I should think about that another time. Think about that later. For now, we'll continue. Given two integers, write a function which returns the greatest common divisor. Code which fills in the blank. So we want to use the Euclidean algorithm. We can use. So I think there is a Gcd built in. All right, let's see. Gcd 2, 4, and 2. I think Clojure does not have a Gcd built in. Okay. We can use, this is considered easy also. It's kind of interesting. Let's look it up. Um, so there's no built-in. That's pretty much what I'm looking for. I mean, that's the, I just got the answer there, but we can do, you can do, so there was a suggestion there to use recur, which I guess we should do that. So AB. All right, fine. Fine. Huh. Okay, so the deal is, what you do, you can use the Euclidean algorithm. That's what we just saw in the post there. It goes, how does it go exactly? You have two values. You divide by some number. How does it work exactly? It's B is equal to some M. Oh, what is it? It's, you can take the smaller of the two values, right? Let's say A, suppose A is greater than B, right? You swap the two if they're not, right? So A is greater than B. So A is some multiplicative factor K times B, we'll call it K sub 1, and plus K sub 2, which is K sub 1 is obviously A divided by B, right? Floor, rounded down, right? The integer division. And K sub 2 is the modular remainder, right? So it's A modulo B is what K sub 2 is. So you actually recurse on those two things. You end up with A, B, and then this is mod AB, right? And the way that works is, we do Clojure integer division. I think it's REM maybe, or quat. Okay, yeah, quat, MN. That's what we want. Quotient. And then you can recur on that. That's the Euclidean, I think it's Euclidean algorithm to find a GCD. You stop when the second value is 0. When you divide, basically when A is divisible by B, when A is divisible by B, that means that your greatest common divisor is B, right? You could end up in a situation, you'll always end up in a situation where B, eventually that's true, and could be 1, or if there is some divisor that is greater than 1, then it'll just be that value for B. Like for instance, 4 divided by 2 would give you 2 rather than 1. So yeah, and you just say if 0 is B, then I don't know, the way around. 0 is B, then you're going to return A, I think. Right, obviously you're not going to return B. What happens if you do this? Yeah, because that actually, when 0 is B, that means that you recursed on the thing where 0 is B. And so you just return A. And then, yeah, pretty simple algorithm. Really kind of cool. Yeah, so let's do... This will use tail recursion and make this algorithm, it'll optimize this algorithm so you don't use stack space. So this will actually end up being like a while loop kind of deal, iterative solution. So GCD of 2 and 4. Oh, okay. Right. Oh, it's also associative, so you've got to have, yeah, okay, let's do that. So we just, this is it's kind of a check. If A is less than B, then, kind of want to do, I could do cond, I guess. It's better than this. Could do a few different conditions at the same time. So if A is less than B, then you want to return the GCD of BA. Right, you reverse the two. A less than B, yes. 0, if B is 0, return A by default. Which is kind of interesting. You're going to end up with the GCD of anything in 0 is itself. Which is true, actually. Because 0 is divisible by anything, right? So that's kind of neat. And then otherwise, we do this. Okay, try that. Try that. Now you can do GCD of 2 and 4. That gives you what you want. Oh. Wait a second. That's not right. Wait a minute. That's not correct. That is not correct. Excuse me. I think these are supposed to be reversed. No. Something went wrong. Right. No. No, this is not supposed to happen at every step. Actually, that's incorrect. This is incorrect. Yeah, that's what went wrong. Is 3 divided by 25 is 8 and 1, and then you said 8 is no, that's fine. 8 and 1, and then you said recur on. Right, so 8 and 1. Recur on 8 and 1. You get recur on AB, right, which is 8, and mod AB is modulo 8 and 1. Should be 0, right? A is 8? No. 8 modulo 1 it should be 0. Yes, you end up with 8 and 0, and then B is 0, so this is just 8. I'm super confused. I did this wrong, huh? What did I do wrong here? Maybe I have the algorithm wrong. Does this work? 25 is equal to 8 times 3 plus 1. Then 8 is equal to 8 times 1. 0. Oh, this is what we're supposed to take. Yeah. No. What? Take this. And then... What? I don't remember. It's been a while. I've done this so many times too. I never remember it. Greatest common divisor. This algorithm. There's a way to prove it. I never quite understood why the proof of this works. The greatest common divisor algorithm. It's an inductive argument though, so it really shouldn't be that difficult to understand. So clearly, so if you take a b times k sub 1 plus k sub 2, and you consider the greatest common divisor of k sub 1 and k sub 2. So we want to show that GCD of k sub 1, k sub 2 is equal to the GCD of a and b. Right? And the way to prove that is you could suppose it's not and show a contradiction, or you could take the properties of GCD and show that it holds for whatever this value is. Both of these values. Right, basically D1 is D2 and they both have the same properties, so it's got to be the same GCD. Well, you can show that GCD is unique, right, because it's the greatest of all the divisors. So there's only one greatest common divisor. And you can show that if there's a divisor that divides, say the greatest common had the greatest common divisor for K1 and K2, you want to show that that will also divide A and it would divide B. So if it divides K1 and K2, obviously it divides A, because A is just a summation of K1 times something plus K2. So clearly this divisor divides this one, right? D1 divides D2. Got it. That's pretty clear. If we could show that D2 then divides D1, then they're equal. So a divisor, and this is really any divisor, or the greatest common divisor. Well, no, that's not. Hold on, I'm getting this wrong. So clearly D1 divides A. Got it. And if we can show that D1 also divides B, then D1 is a divisor of A and B. And then that means that D1 is less than or equal to D2. I think that's what we want to show. If it's divisor of B, how do we get divisor of B? Basically show that D1 times some constant equals B Yeah, that makes D1 a divisor of B. So we would say there's some, alpha over D1, which is K1, or other way around, B1 alpha K1 plus beta K2, or D1, excuse me, D1 plus beta D1, that's equal to A. And we want to say that B equals some, so if we subtract A minus beta D1 over alpha D1, that means alpha D1 divides B. Which I think implies that alpha divides B or D1 divides B. I think it means both, actually. Right, that implies both. Yeah, because you could that implies both. Because you could restate this as, well, not necessarily, right? That means that it's A minus beta D1 over D1 over alpha, which is then also A minus beta D1 over alpha over D1. But there's no guarantee that this is an integer and that this is an integer. Well, if these aren't integers, then dividing by an integer is not going to make it an integer, right? I think by the nature of this being integer division that we're dealing with, I think it does imply what we're looking for, though that's not so obvious to me why that would be the case. Somehow we end up here with D1 divides A and D1 divides B. I'm not really clear on that. But that would make D1 less than or equal to D2. In fact, yeah, it's a divisor of A and B. So now I've got to show the other way around that D2 is a divisor of K1 and K2, the GCD of K1 and K2. Or it's a divisor of K1 and K2. I don't know, man. It's not so obvious. How do I know that this is a divisor of A and a divisor of B, the GCD of K1 and K2? How do I know that? How do I know that? I mean, being a divisor of A is kind of obvious, but being a divisor of B is not so obvious. Maybe we should do it that way. We could say, clearly this is a divisor of A, right? I could say D1 is equal to sum A over B alpha plus beta. Alright, let A equal some C D1, right? And then now you've got B alpha D1 plus beta D1 equals C D1, and we want to show that B alpha D1, which is then C D1 minus beta D1, end up with B alpha equals, you can actually divide D1 out of here completely, and you end up with B equals C minus beta over alpha. Right? Yeah, I feel like we end up with like sort of circular reasoning if we say that B is, if D1 is divisor of B. It's not so clear to me. I don't know, maybe we should say alpha is equal to C minus beta over B. Well, maybe you can say this, like beta alpha equals C minus beta, or B alpha. So that means that what is this? This is D1 is divisor of B. This is, you know, these are both divisors of B, right? D1 and C are divisors of B. This says that B divides C minus beta and alpha divides C minus beta. Which doesn't necessarily tell you much about, geez, I probably should just look up a proof for the Euclidean algorithm. I feel like I should be able to just whip it offhand by now, because I've seen it so many times, done it so many times. But I don't know, I guess not. Shucks, man, shucks. How do we do this? C minus beta, alpha C minus beta. Doesn't really help us that much. I mean, yeah, alpha is some C minus beta times some value. Technically, it's actually D sub 1. No, it's not. You know, I don't know. How, I want to say some proof by contradiction somewhere in here. I don't know, man. I don't know, man. Also, I think the algorithm is not really correct, right? Hold on, what do we do? Is my algorithm just wrong? So 25 is 3 times 8 plus 1. Then the quotient we end up with is between 25 and 3. We end up with 8. And end up with 8 times 1 plus 0. That is a tricky thing. I know the greatest common divisor is a 1, but 8 times 1. Oh, we should end up with a 1 here. Alright, this is B is 0, you return A. No. I guess you return the quotient. Of A. Hold on, what? I think it's not if b is 0. I think if I gotta go one step before. Mod a and b is 0. Maybe this is the issue. Also, the proof I don't have here either. Should have that like on hand. Oh, come on, really? A should be 1 here, no? I'm so confused. Isn't B is 1? Then you have 1 and 0, right? B is 1. That's extremely confusing. A is always greater than B, right? So A becomes this value, B becomes this value. How the heck did I get the wrong answer here? Confusing things here. 25 divided by 3 is 8 and 1, right? Quotient is 8, modulo 1. Then 8 divided by 1 is 8. Quotient is 8. Oh, that's why. Yeah. No, the quotient is 8 again. 0. And then you have... Oh. I guess you return... No, because the quotient is just 8. You shouldn't... Shucks. So really, yeah, it's when... I think it's the other way around. I think it's if mod AB, then you return B. I think that's what we want. It's confusing. Super confusing. There we go. Okay. Kind of want to go one step ahead. Yeah, so actually that GCD argument that I had is not correct. It's when this is finally modulo 0, when they're finally divisible one by the other, right? When you finally have B is a divisor of A, then return that divisor of B. You don't want the quotient anymore. Kind of want to see a Euclidean algorithm proof now. Anyway, so we can put this in here. Condition A less than B, then you want to recur or just call GCD of BA. Otherwise, you want check if this is 0. If you take modulo A divided by B, if it's modulo 0, then you're going to want to return B, right? If B is a divisor of A, then B is the greatest common divisor, right? That's your base case. And then finally you say, if you're not at the base case, you're going to recur with quotient of a divided by b and the remainder of a modulo b. Let's see how that goes. Oh. And a couple more things is otherwise. So any key will be truthy, so you'll have this default value at the bottom. Oh, you gotta be kidding me. Serious? What? Okay. What am I doing wrong here? I don't know, man. That's why you need a proof. That's why you need a proof. What happened? 1, it says. You're kidding. Yeah, somewhere in there. I think this condition in between is causing me problems. This must be the problem. This should really only happen once, I think. On the first execution. Yeah, you don't want to do that recursively. It doesn't work like that. It doesn't work properly. Maybe I can call an inner function here. Like, I don't know, can we do it this way? Kind of want to do something like self-contained. Gcd helper, maybe. And that would look like the following. Which would be a less than b. So no. So that's the helper that gets. We call the how we call the helper. We'll say if a is less than b, then GCD helper of BA, otherwise GCD helper of AB. Right? More or less what we want. And there's this condition, says just an if, I think. And we can call this does this even work? Does this work? I don't know. What I'm wondering is this function and this if statement. Oh yeah, no, this doesn't have, it's not named. This should be fine. How does this work? Does this work? No. Of course it doesn't. Yes. Okay. Now the example they gave was here. 1023 and 858. No. No, you're kidding. No. 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 Maybe I need to. Unless I did this incorrectly. I may have just. Oh, that's why. Okay, that makes sense. Can we do this? Please do this. Like I won't be able to. I don't. Oh no. I don't know. Okay. Okay. Let's call this a non. This is this is interesting. The bindings, how the bindings are set up here. This is supposed to be 33? Are you kidding? You're kidding me, right? Is this real? Am I messing this up this badly? Correct? Is my algorithm just wrong? It is. Oh, nice. Nice. Perfect. This is great. I don't know what I did wrong. I don't know. I don't know. I guess if I perform the algorithm right, so 1023 and 858. 1023 and 858. Times 1. 165. I end up with 858. Now, I think I did. I think maybe this is the problem that I have, is that I should be taking this value, not. It's. I think the issue is it's not supposed to be the quotient of A and B. It's supposed to be just. Oh, that could be the issue I was having before. Why I was getting things wrong. It could be not K1, K2. It could be what's left over. This is B, A, and B, so it could just be B. Oh, that's probably the issue. That might be why. That may be the problem. I forgot the algorithm. Forgot the algorithm. Which is much more likely because I don't memorize these things. Don't even, oh, okay. Yeah, that was the problem. Okay. No, that's fine. No, that's okay. I don't, whatever. Not a big deal. Not even, no issue. Not a problem. What is even going on? I don't know anymore. What am I even doing here? What the heck is going on, man? Jeez. Okay. I think the original idea I had was fine. So it's the GCD of AB is equal to the GCD of B and A modulo B. Yeah. Right. Nice. Alright, I got 13 minutes here. Yeah, 2 problems in 2 hours. Seems good. Not bad. How do you prove that the GCD of A and B is equal to the GCD of B and A modulo B? D1, D2. So first, let's show that D2 is less than or equal to D1, or D2 divides D1, one or the other. So if we say, clearly, if we're a divisor of B, and we're a divisor of A and B, well, first things first, B is less than A, right? Now B is not necessarily a divisor of A. D2 divides B, and D2 divides B modulo A, which is basically B integer division A minus B times A. Or, what is this? What does that even mean if D2 divides A modulo B? What is A modulo B? Basically means, like, let's let K equal A modulo B. That means that B times some constant, we'll call it alpha, plus K is equal to A. And D2 divides this K. Right. Call it alpha 1. And you have K1 alpha 1. And you have B is equal to it's supposed to be K1 here, I think. K1 alpha 2 K2. And it continues this way. And somehow, right, so we can do an inductive argument where, right, if we can show that this is true, then this is you know, this is what we want. Problem with this though is, how do we show this, that these are equal to each other? Well, can we at least show B A modulo B greatest common divisor? Like, we could show D1 divides D2 and D2 divides D1, then we're good. Okay, we've got it. Got what we want. How do I even show that though? Well, we do know, okay, so we have this equation, right? B alpha 1 plus K1. We know that there's some, we'll call it Q1, Q2, right? So Q1 times D1 equals, or D2 is equal to B. And some Q2 times D2 is equal to K1. Right? It's got these two different, because this is the divisor of B and K. Just call it K, alpha and K, it doesn't matter. So we can rewrite this as A equals some B, which is Q1 D2 alpha plus Q2 D2, yeah, Yeah, just like that. And what that implies is if we show D2 divides A and B, then D2 is a divisor of, then D2 is less than or equal to D1. Maybe we can start with that. So let's just try to show D2 is less than or equal to D1. It's not a divisor, but it's like it's close. It's something to work with. So now that may not be. No, it must be true. No. Well, they're equal, right? We're going to show that they must be equal, so they've got to be less than or equal to, right? That holds. So we can show that. So D2 Q1 plus Q1 alpha plus Q2 gives you A. Clearly, D2 divides A. Or, yes, D2 is a factor of A. D2 divides A. Yeah, correct. Okay, sweet. Got that far. Now, if we can show that D2 is also a divisor of B, it is a factor of B by definition, right? We know it divides B. And D2 divides B, which implies D2 divides the GCD of A and B. Or rather, D2 is less than or equal to. D2 is a divisor of. Yeah, D2 is a divisor of AB. Okay, done. Right, done. Okay, that actually follows very easily. I don't know why I struggled so hard to get that before. I think before because I had the wrong algorithm. Right, it's B and A modulo B that you recurse on. So clearly, actually D2 being a divisor of A and B is being a common divisor of A and B follows easily, right? Because D2 is by definition divisor of B, and then we can use this formula to show that D2 is also a divisor of A. Okay, great. So that means that D2 is less than or equal to D1. Now we want to show that D1 is less than or equal to D2. How do we show that? Well, we know that D1 is divisor of B and D2 is a divisor of B. So what does that mean? Well, there's some relationship between D1 and D2, certainly. If we can show that D1 must divide B and A modulo B, well, clearly we have, so we have D1 divides A and D1 divides B implies that D1 divides B, right? So now we just need to show that D1 divides A modulo B. That's the thing that we were kind of stuck on here, right? So A D1 divides K. How do we get there? Well, we can write A B alpha plus K and we want to say what is the relationship between K and I guess A and B or D2? D2 divides I want to show that D1 divides K. That means that we want to get D1 times some C equals K. Okay. Here we have K is A minus B alpha. Right. So we want to factor D1. Yeah, does that hold? Well, D1 divides A and B. So you can just factor out D1 with, I don't know, I'm an OP PQR, we'll call it R1 minus R2. Does that work? Which gives us D1 divides K. Yeah, I think so, right? A equals D1 R1, B equals D1 R2. Am I just going crazy? Like, is this a lot easier than I realized? Is this just like way easier? And then that implies that D1 divides K, D1 divides B, D1 is less than or equal to D2. Am I nuts? Am I nuts? Wow, really? There's no way. There's no way it's that simple. There's no way it's that easy. Is it that easy? It might just be that easy. Then you can use an inductive argument after that. Yeah. We got only a couple more minutes here. Let me try this one more time. So you got A equals some alpha times B plus K, where K equals A modulo B. Now, there's no way that we just did is correct, right? I think there's no way. There's no way. What is going on? So D1 divides A and D1 divides B implies that D1 times some R1 equals A and D1 times R2 equals B, right? And then if you take, right, then you end up with, which then gives you D1 R1 equals alpha D1 R2 plus K, and you get K equals D1 of R1 minus alpha R2, right? And which implies that D1 divides K and D1 divides B, which implies that D1 is a common divisor of K and B, which means that D1 is less than or equal to D2. And you perform the same operation the other way. D2 is divisor of B, and D2 is divisor of K, which gives you B equals some Q1 times D2, and K equals some Q2 times D2, which then gives you A equals Q1 D2 alpha plus Q2 D2, which then means that D2 Q1 alpha plus Q2 equals A, and D2 divides A, which then implies, and D2 divides B, which gives you D2 is then less than or equal to D1. Right, it's a common divisor of A and B as well. Therefore, D2 equals D1. So the greatest common divisor. Now, the problem with this, though, the thing that's missing with this proof is that this doesn't need to be modulo. This K does not need to be A modulo B. right? That's actually really critical key thing to note here. It's really important. Doesn't prove that the algorithm is correct. It just proves that the GCD of A and B is going to be the GCD of B and any K, where now the problem here, that K can be arbitrary, because as long as K is some remainder for some arbitrary alpha where this relationship holds. Now, this relationship always holds when you're dealing with A modulo B, so I guess it works, but it actually is not necessarily the case. Like, you could do, like, this is the maximum possible alpha, like, but you could do A equals, let's say, beta B plus K, right? And the relationship, and we'll do K prime, and the relationship could be basically this is it's alpha it would be alpha minus beta minus 1 equals, I don't know, 1. So you could basically, I want to swap alpha with 1. So alpha is some non-zero, some non-zero positive integer. It's actually going to be A divided by B. It could be 1, but let's say like, with 25 and 3 instead of 8, 3 and 1, you could have had, which, by the way, this, you don't take the alpha, you take 3, and that was what was missing before. What is this? You don't take the 8, you take the 3, right? And then you take the 1, and that's 3. And so now here you would take 1. Yeah. But you don't even need to go to this step. You just take B. Or you just take A. Just 1. Anyway. But my point is, you could do, this proof works, like you could do 4 times 3 plus 13, right? And you get 12 plus 13 is 25. And then now you still take 3, but now it's 3 and 13. And B is no longer greater than A, right? Like A is, B, yeah, B is this value over here. It's still the same GCD, 3 and 13, but it's very different, right? It's totally different now. You still get the same GCD, it doesn't matter, which is really weird how that happens, but still get the same GCD. But now it's still 3 and 13, which this doesn't make sense anymore, though. Like, that's kind of the problem, is that you can't inductively recurse if K is not smaller than B. Like, you kind of need that part. So you need, while this statement is true, for any K where this holds, you can't form an algorithm without K is necessarily less than B at every step. Excuse me. And that's critical to actually proving that this algorithm halts, I guess. That's pretty much what you need to prove, that this forms a basis for an algorithm that halts. Yeah. Which is really interesting. Like, that's kind of like, it's almost trivial to prove that this is true, because but the proof is true for any K where this relationship holds, and it doesn't give you an algorithm to actually compute K, or actually compute doesn't actually give you an algorithm to compute the GCD of A and B without simultaneously decreasing both of these values. And obviously it won't work unless this is larger than the other. But you always have it, as long as you take something modulo B, or as long as you take this modulo B, you end up with something that's less than B. And so you can recurse until you're down to sort of some x0 base case. And also you have it actually works out really nicely that it's just a single division split into a modulo and quotient piece. Like that comes out, it's like very sort of elegant that happens that way. Just so happens that you can take something, you can take A modulo B and then end up B is then what is it then the other value to consider. Well, yeah, you could just take A modulo B, I guess, bottom line. Works out nicely. It's kind of odd, kind of weird. Yeah, it works. It works. Yeah, A modulo B is guaranteed to be less than B, always, no matter what B is. Yeah, or A modulo B is always guaranteed to be less than, no, well, B, yeah. That's kind of interesting. This is logarithmic then, because, no, not necessarily. I don't know what it is. Euclidean, I think it's logarithmic, right? Because it's a division, A to B, and then you go, B is always moving to something that's sort of modulo, so B is sort of always moving to something modulo its former self. I wonder if there's a time complexity analysis for what Euclidean algorithm. I think it's logarithmic, but I don't know. Codility. Subtraction by division. It's super simple once you've got it, but proving it's kind of not the easiest thing. Denote A, B pairs, 4 steps, then B of I is greater than or equal to Fibonacci I minus 1, where Fib is ith Fibonacci number, inductive proof. For more steps. Approximated by this. Thus the time complexity is logarithmic based on the sum of A and B. Log A plus B. Really? Yeah, so this is, okay, very simple proof, hence, okay, recursively call a function while A is not divisible by B. Denote pairs which the above algorithm performs I steps, then B sub I is greater than or equal to fib of I minus 1, where fib of I is the ith Fibonacci number, inductive proof. b sub I is greater than or equal to the Fibonacci of I minus 1. Where does that come from? What? For more steps. A of k equals b of k plus 1, a k minus 1 equals b of k. B of k minus 1 equals a of k modulo b of k, so a of k equals q of b of k, k plus... Oh, for some q greater than or equal to 1, so b of k plus 1 is greater than or equal to b of k plus... Oh, those are Fibonacci numbers. Oh, look at that. Oh, that's really cool. Oh, that's a really clever approach. So what they're suggesting is, if you were to go backwards, then you would have a sequence that is actually greater than the Fibonacci sequence. Oh, which means that this has to be decreasing at least as quickly as the Fibonacci sequence is, and the Fibonacci sequence is bounded above logarithmically, or rather is exponential. So yeah, it has to, yeah, so you have to be increasing at least as quickly as the Fibonacci sequence is increasing, and the Fibonacci sequence increases exponentially. So if you reverse that, then you're moving logarithmically. Oh, that's so clever. Wow, that's a really clever way to do this, to prove it. I didn't even think of that. Whoa. Wow, okay. I feel like I should know that, but for whatever reason, it didn't strike me as true. Linear in the number of input digits, which is another way of saying it's logarithmic. Polylogarithmic factor can be avoided by instead using a binary GCD. Wow. So you can even refine this even more beyond logarithmic and consider something polylogarithmic and use binary GCD. Stein's algorithm computes GCD. Simple arithmetic operations than the conventional algorithm. Replace division with arithmetic shifts, comparisons, and subtraction, although the algorithm was first published by the physicist and programmer Stein in 1967. So they figured this out 52 years ago. Wow. Jeez, man. There are some days when I'm studying this stuff and I feel like I'm just like looking at the graves of programmers past, something like that, because it's like I'm in such old territory, like such old, like I'm so far from the cutting edge of research, it's like I'm dead, you know. And that's also how I feel about, because like people don't watch my stream when I do this stuff, like they're like, yeah, this is not really worth time because it's super old what you're going over. It's like, yeah, it's old news. God, I suppose that's true. May have been known in 1st century China. Wow. Known for a long time, this algorithm, Stein's algorithm. So you use, okay, so you use bit shifts instead of integer, instead of subtraction. You use bit shifts and subtraction instead of just a simple division. So GCD of 0 and v is v because everything divides 0 and v is the largest number that divides v. Similarly, GCD of u and 0 is u, and GCD of 0 is not typically defined, but it's convenient to set it to 0. U and v are both, if they're both even, then this is going to be twice the GCD of these two bit shifts because 2 is a common divisor. If u is even and v is odd, then GCD of u equals the GCD of u divided by 2v because 2 is not a common divisor. Right, so 2 is not a common divisor, so you can just divide u Similarly, if u is odd and v is even, then you can do the symmetric case, the mirrored case, symmetric case. Okay. Okay, so these are the bit shifts. And then if u and v are both odd and u is greater than or equal to v, then the GCD of u and v is going to be the GCD of u minus v divided by 2 and v. Okay, how does that work? That part we gotta think about a little bit. If both are odd and u is less than v, then GCD of u and v is equal to, right, of v and u. So the u greater than or equal to v. So you could swap the two, right, such that u is always greater than or equal to v. These are combinations of one step of the simple Euclidean algorithm, which uses subtraction at each step, and an application of step 3 above. The division by 2 results in an integer because of the difference of two odd numbers is even. Oh, okay, so you use the traditional Euclidean algorithm, and this step is performed. So u is greater than or equal to v, and you say, okay, take the difference between u and v. So it's one subtraction step of the Euclidean algorithm. You can do that as well. You don't need to do... oh, that's very interesting. So... which, by the way, I would actually swap v and this value, because this, we know this is going to be less than u. No. U minus v is not necessarily less than v. That's not necessarily true. This part, I gotta think about it, why this is true. Repeat steps 2 and 4 until u equals v, one more step until u equals 0. In either case, the GCD is 2 raised to the kv, where k is the number of common factors of 2 found in step 2. 2 raised to the k times v, where k is the number of common factors of 2 found in step 2. Algorithm requires quadratic worst case time, where n is the number of bits in the larger of the two numbers. Although each step reduces to at least one of the operands by at least a factor of 2, the subtract and shift operations take linear time for very large integers, although they are still quite fast in practice, requiring about one operation per word of representation. An extended binary GCD analogous to the extended Euclidean algorithm is given by Knuth, along with pointers to other versions. So there's the extended Euclidean algorithm. So this is logarithmic as well, but it's faster than the other Euclidean algorithm that we considered. And this is quadratic in the number of bits, which is still logarithmic, but it's, you know, right, quadratic in the number of bits of the largest number. Steps 2 to 4. So this part, I want to get 4, I want to consider, and then I also want to take a look at what the extended Euclidean algorithm means. We'll do that shortly. There's an even faster way to do. I think I need to end I think I need to end stream now, though, and just so that way this video is not like super long. So if u and v are both odd and u is greater than or equal to v, then GCD of u v is equal to the GCD of the difference between u and v divided by 2 and v. Both are odd, then this is just symmetric, right? These are combinations of one step of the simple Euclidean algorithm, which uses subtraction at each step and an application of step 3 above. So they're both odd. The difference is even and odd. So you end up, right, you can just apply this. You can go right to here. But you would say this is the GCD of u and v is equal to GCD of u minus v and v. That's the normal Euclidean algorithm with subtraction rather than division. Right. You can say, like, this algorithm still holds, this GCD thing still holds. You don't necessarily need to use modular arithmetic, right? You can do what do they call that? Actually, some explanation for this is basically you could do, this is A minus B repeated until you're in the range of B, right? Until you're between, until you're less than B but still greater than 0. That's sort of like repeated applications of the subtraction version of the Euclidean algorithm. But you can also show that Gcd of AB is equal to the Gcd, again we're assuming, of A minus B and B, right? This proof is the same for this case as well as this case. You just need to have this formula, right? So A equals alpha B plus K. So A equals alpha B plus K means, so K is A minus B, and alpha times B plus K. This just implies that alpha minus B equals 0 times, right? Which then gives you alpha equals 1. It just means that alpha is 1 in this instance. But alpha could be anything. And obviously the GCD. Yeah, I as long as you swap the places correctly, right? A minus B and B, and as long as the smaller of the two is the part that you're sort of placing to the right, and that you're letting be K, as long as K is the smaller of the two. But yeah, this holds too for the same reason, same rationality, is that if D1 divides A and B, then D1 divides A and D1 divides B, excuse me, and D1 divides B already, so then you just need to show that D1 divides A minus B, which it does, because these values satisfy this equation, the one that we gave here, right? Alpha and K. Yeah, so you can show that this holds too, easily. And then because this holds, then you can just jump to this part right here. Similarly, this part. So that's pretty cool. So you just repeatedly apply each of these cases, right? If they're both even, you recurse here. If they're odd and even, you recurse here. If they're both odd, then you recurse here. And finally, you end up with the GCD at the end of it all, until they're equal to each other, or until one of these is 0. GC is 2 times KV, where K is the number of common factors found in step 2. Really cool. So this is how you end up with, right, sort of constantly dividing by 2 in each step. And they explain why it's quadratic. I think it's because it could be, the bit shifts are sort of linear in the number of bits. And so that ends up being you have one iteration per bit, and then each iteration requires a linear number of operations per bit. So you end up with a linear number of linear executions, linear time executions. Now, I wonder if you could do this in parallel. I don't think you can, because you need to know at each step the branching. But it'd be cool if you do it in parallel. Iterative version in C. Yeah, so I understand now. A few different cases. Recursive version is a lot simpler than the iterative version. But that's kind of cool. You can do it iteratively as well. That's kind of wild. Didn't realize you could do it iteratively. Oh, I guess you shift out all of the powers of 2, something like that. And then at some point u is always odd. So you can operate. Oh, that's kind of cool. And you bit shift v. Oh wow, that's amazing. I should think about that some more. Come back to it another time. How that works. How you can change this algorithm to be an iterative algorithm rather than a recursive algorithm. That's pretty cool. Copy and value proved that in theory, binary stitching can be about 60% more efficient. On average, this algorithm modestly outperforms the traditional implementation. Performance is the same. Considerably more complicated to code given the widespread division instruction in all modern microprocessors. Some processes division instruction may be a lot slower. Real computers operate on more than one bit at a time, and even assembly language implementations compete against carefully designed hardware circuits for integer division. Overall, Knuth reports a 20% gain on a version of mix. Arbitrary precision arithmetic. Neither the Euclidean algorithm nor the GCD are fastest, as they both take that time that is quadratic function of the number of input digits. Instead, recursive methods that combine ideas with the Schoenhaug-Strassen algorithm for fast integer multiplication can find GCDs in near linear time. Whoa! Arbitrary precision, neither are faster, but recursive methods with Schoenhaug-Strassen can find GCDs faster. Interesting. So that's arbitrary precision. You can do that. Algorithm for computing the GCD of 2 numbers was described in ancient China. Okay, is there a faster way to do GCDs? Extended Euclidean algorithm? Also the coefficients of Bezout's identity. Oh, okay. So not only does it calculate the GCDs, but also the ax plus by equals GCD of AB, which is, this is the oh, wait a minute. Certifying algorithm. GCD is the only number that can simultaneously satisfy this equation and divide the inputs. Allows one to compute also with almost no extra cost the quotients of A and B by the greatest common divisor. Is this just like the last? Wait a second. Ax plus by equals GCD. I think this is. Huh. Wait a minute. I want to say it's like the last step of the Euclidean algorithm. You could just report these values. The GCD is 5. Like, let's say like A and B is 20 and 5, right? GCD would be 5. 20 times x plus 5 times y equals 5. Could do like 1 and -3. I've actually computed the extended Euclidean algorithm, but I don't remember how to do it. I don't remember at all. Okay, so you can prove the Bezout's coefficients as one of the 2 minimal pairs of Bezout coefficients. Also means that the algorithm can be done without integer overflow when A and B are representable integers. Interesting. 2 minimal pairs. One of the 2 minimal pairs. I guess you gotta kind of walk through all of this again. Sequence of remainders, sequence of quotients. And basically, I think the suggestion is that the Viso pairs are a pair of quotients and remainders. It's one of the last few quotients and remainders. And I guess this Q sub I has got to be negative, right? Okay, I guess that makes sense. One of these have to be negative, right? There's no other way. Yeah, this is something I studied at uni. Actually, one of the like intro to what is it? Intro to applied math classes. They went over this extended Euclidean algorithm. I thought it was really easy, because I guess it kind of is, but understanding it, like, it's not that simple, but it's a relatively simple thing. Yeah, that was like 6 years ago, 7 years ago I did that. It's like a dummy, man. It's probably, yeah, something like 7 years ago. I don't know. Didn't really fully understand it. I mean, I understood it, but I don't remember it, you know? I didn't really get the full... Didn't really get the full thing either, right? Like Viso's identity. Yeah, I didn't really understand this, actually, after all. Like, why, what the significance of this is, and I don't know. I don't know why we're doing it. We're just learning it. I don't know, man. Anyway, Schoenhaag-Strassen. Asymptotically fast multiplication algorithm for large integers. Runtime in bit complexity is in big O. N log n log log n for 2 n-digit numbers. Use recursive fast Fourier transforms in rings with 2 raised to the n plus 1 elements. Specific type of number theoretic transform. Fast Fourier transforms. I don't know what those are. Schoenhaag-Strassen algorithm was the asymptotically fastest multiplication method known from 1971 until 2007, when a new method, Fourier's algorithm, was announced with lower complexity. However, currently only achieves an advantage for astronomically large values and is not used in practice. Oh, okay. Practice, a Schoenhaag-Strassen algorithm starts to outperform older methods such as Karatsuba and Toom-Cook multiplication for numbers beyond 2 raised to the 2 raised to the 15th to 2 raised to the 2 raised to the 17th, 10,000 to 40,000 decimal digits. The GNU multi-precision library uses it for values of at least 1728 to 7,808 64-bit words, 33,000 to 150,000 decimal digits, depending on architecture. There is a Java implementation of Schoenhaag-Strassen, which uses it above 74,000 decimal digits. So over 10,000 digits. Start seeing. Yeah, but how often are you using numbers that have 10,000 digits? You know? Applications of the Schoenhaag-Strassen algorithm include mathematical empiricism, such as the Great Internet, Mersenne prime search, and computing approximations of pi, as well as practical applications such as Kronecker substitution, in which multiplication of polynomials with integer coefficients can be efficiently reduced to large integer multiplication. This is used in practice by GMP ECM for Lenstra elliptic curve factorization. Kronecker substitution, which multiplication of polynomials with integer coefficients can be efficiently reduced to large integer multiplication. This is used in practice by GMP DCM for Lenstra elliptic curve factorization. Holy smokes. Discrete Fourier transform sequence or its inverse DFT. IDFT, Fourier analysis converts a signal from its original domain, often time or space, to representation of the frequency domain and vice versa. DFT is obtained by decomposing a sequence of values into components of different frequencies. This operation is useful in many fields, but computing it directly from the definition is often too slow to be practical, and FFT rapidly computes such transformations by factorizing the DFT matrix into a product of sparse, mostly zero factors. Managed to reduce the complexity of computing the DFT from quadratic, which arises if one simply applies the definition to n log n, where n is the data size. The difference in speed can be enormous. Long data sets where n is maybe in the thousands of millions. Process of round-off error. Many FFT algorithms are much more accurate than evaluating the DFT directly or indirectly. There are many different FFT algorithms based on a wide range of published theories, from simple complex number arithmetic to group theory and number theory. Fast Fourier transforms, widely used for applications in engineering, music, science, and maths. The basic ideas were popularized in 1965. Some algorithms had been derived as early as 1805. Gilbert Strong described the FFT as the most important numerical algorithm of our lifetime. It was included in top 10 algorithms of the 20th century by the IEEE magazine, Computing and Science and Engineering. Best known FFT algorithms depend on the factorization of n, but there are FFTs with n log n complexity for all n. Even for prime n, many FFT algorithms only depend on the fact that e raised to 2 pi I divided by n is an nth primitive root of unity, and thus can be applied to analogous transforms over any finite field, such as number theoretic transforms. Since the inverse DFT is the same as the DFT, but with the opposite sign in the exponent and 1 over n factor, any FFT algorithm can easily be adapted for it. I should probably study this at some point. I know I did something with FFTs way back when, very briefly. I feel like this is something I should know how to do. Gilbert Strong. Gil Strang, Strong. Mathematician. He's still around, right? Yeah, it's 84. Holy smokes. Why do I feel like it sounds familiar? MIT, UCLA, finite element theory, calculus of variations, wavelets analysis, linear algebra, 7 textbooks and 1 monograph. MathWorks professor of mathematics at MIT. Teaches Introduction to Linear Algebra and Computational Science and Engineering. His lectures are freely available through courseware. Monograph. Our exhibition on a single subject or an aspect of a subject, often by a single author or artist, and usually on a scholarly subject. Library cataloging monograph has a broader meaning, that of a non-serial publication complete in one volume, book, or a definite number of volumes. As it differs from a serial publication such as a magazine, journal, and newspaper. In this context, only books such as novels are monographs. Monographia surveys the state of knowledge in a field. The main purpose of a monograph is to present primary research and original scholarship, ascertaining reliable credibility to the required recipient. This research is presented at length, distinguishing a monograph from an article. For these reasons, publication of a monograph is commonly regarded as vital for career progression in many academic disciplines. Intended for other researchers, bought primarily by libraries, monographs are generally published as individual volumes in a short print run. Britain and the US, what differentiates a scholarly monograph from an academic trade title varies by publisher. Generally, it is the assumption that the readership has not only specialized or sophisticated knowledge, but also professional interest in the subject of the work. Interesting. Huh. I don't really know what that means. It's a specialist work of writing or exhibition of it on a single subject or an aspect of a subject, often by a single author, usually on a scholarly subject. Okay. And cataloging has a broader meaning. Okay. I'm not really familiar with that at all. I don't really understand. I probably should end the stream here. Take a break. Gilbert Strang. For some reason he sounds familiar. Is there images of Gilbert Strang? He seems so familiar for some reason. I don't know why. I feel like I've seen stuff that he was in. I don't remember why exactly, or maybe even. Oh yeah. I watched one of his lectures. Yeah, that's why. Because I watched one of his lectures in when I was in uni many years ago. One of his linear algebra. One of his linear algebra. Of course, I was like, why does he seem so familiar? This name, because one of his MIT Open Courseware courses. I tried to do the whole course when I was at uni at Stony Brook because I wanted more information about linear algebra. I took his course in the summer. I didn't take it, but I was, oh my goodness, now I remember. The summer before I was supposed to take linear algebra at Stony Brook, I went through as much as I could of his course at the MIT Open Courseware course in the summer. That was so many years ago. That was like, we're talking like 2011. I did that. And strong. That was, yeah, because I watched so many of his videos. I spent so much time on it, or it felt like a lot of time during the summer. Oh, no kidding. Yeah. Smart cookie, this fellow. Smart cookie. Yeah, I really appreciate MIT OpenCourseWare. It's so good. It's so good. There's some things in this world I appreciate a lot. That's one of them. That's one of them. Leopold Kronecker for determining the coefficients of an unknown polynomial by evaluating it at a single value. If px is a polynomial with integer coefficients and x is chosen to be both a power of 2 and larger magnitude than any of the coefficients of p, then the coefficients of each term can be read directly out of the binary representation of p of x. Determining the coefficients of an unknown polynomial by evaluating it at a single value. P of x is a polynomial with integer coefficients and x is chosen to be both a power of 2 and larger magnitude than any of the coefficients of p, then the coefficients of each term can be read directly out of the binary representation of p of x. Holy smokes, what? One application is to reduce the computational problem of multiplying polynomials to the potentially simpler problem of multiplying integers. P of x and q of x are polynomial with known coefficients, then one can use these coefficients to determine a value of x that has large enough power of 2 for that the coefficients of the product to be read off of the binary representation of the number p of x, q of x. Since p of x and q of x are themselves straightforward to determine from the coefficients of p and q, the result shows that polynomial multiplication can be performed in the time for a single binary multiplication. Whoa! Algebra. Can I find paper on Kronecker substitution? Can I like perform that? Like I need to practice with that to understand what they're talking about. That seems really powerful. Seems extremely powerful. I don't know what you can do with it, but it seems like you can do some really fast multiplications, I guess, or operations. Wow. Hadamard product. Properties. There's so much reading to do, man. So much studying to do. It's not enough time. I wish I could study more things. I should stop here though. Right. Failed the unit test. Nice. It's because I'm a dummy. It's because I'm a dummy. Because I am a dummy. Oh boy. How about that? How does that work? Nice. See what other solutions people have. Oh, Leinster elliptic curve factorization, or the elliptic curve factorization method, is a fast sub-exponential running time algorithm. Sub-exponential, interesting. For integer factorization, which employs elliptic curves. For general purpose factoring, ECM is the third fastest known factoring method. second fastest is the multiple polynomial quadratic sieve, and the fastest is the general numbers field sieve. Elliptic curve factorization is named Hendrik Lenstra. Practically speaking, ECM is considered a special purpose factoring algorithm as it is most suitable for finding small factors. Currently, it is still the best algorithm for divisors not exceeding 50 to 60 digits, as its running time is dominated by the size of the smallest factor p rather than by the size of the number n to be factored. Frequently, ECM is used to remove small factors from a very large integer with many factors. If the remaining integer is still composite, then it has only large factors and is factored using general purpose techniques. The largest factor found using ECM so far is 83 decimal digits and was discovered on September 7th, 2013 by R. Proper. Increasing the number of curves tested proves the chances of finding a factor if they are not linear with the increase in the number of digits. Random elliptic curve. This equation, non-trivial point. This can be done. Sure, the point is on the curve. Define addition of 2 points on the curve. Define a group. This is kind of complicated. What's the time complexity though? I don't know. Elliptic curves. I don't know. Yeah, it would take a lot of time for me to really understand this. Oh, extended Euclidean algorithm. Huzzah. Huzzah. What are we looking for here? There we go. It depends on the size of the number of smallest prime factor. It can be represented by the exponentiation of square root of 2 plus constant term times the square root of the natural log of p times the natural log of the natural log of p, where p is the smallest factor of n, or LP half square root of 2 in L notation. It's analogous to big O notation. L notation. Wow. Wow. P is smallest factor of n, or L half square root of 2 in L notation. I don't know what L notation means exactly, but this is pretty fast. This is pretty fast. I think this is L notation. This is equivalent to L notation, where L sub p, where p is the smallest factor of n. Wow, well, if it's a prime number, shouldn't this be really fast? Would this be really fast if well, I don't know, probably not, actually. But it's pretty fast with respect to, well, yeah. I mean, it's not prime, but it's got like two prime numbers, two very large prime numbers that multiply to create the number. Basically, this is digits, the number of digits in p in the smallest prime factor. Square root of that, though, which is not too bad, I guess. Yeah, it's like proportional to the square root of the digits in p, the smallest prime factor of p. Just kind of like the fourth root of p, I guess, if it's in the worst case where, well, no, if the smallest prime factor is a 1, no, I guess 1, not including 1, as being the smallest prime factor, so the worst case would be if it's a prime number, the smallest prime factor is itself, then it's the number of digits, right? Square root of the number of digits in p. Proportional to the square root of the number of digits in p. I think that's what this means in terms of, like, to really sum it up. But it's pretty good, I think. It's fast. Relatively fast. Kronecker substitution. But yeah, you can actually factorize pretty quickly. It's just you can't factorize, I think, fast enough, something like that. I forget exactly what the issue is with why public-private key encryption works, despite being able to factorize relatively quickly. Oh no, never mind. I take it back because it's exponentiated. This is exponentiated. That's why. Wait, what am I missing? I don't know. I think isn't there? Yeah, you can't find something that's linear in the number of digits. Hold on. What am I missing here? I'm missing something. Something's not right. I'm missing something. Yeah. Sub-exponential. Right. Okay. There are things that are sub-exponential, but the only algorithm that's proportional to the number of bits, that's polynomially proportional number of bits, are Shor's algorithm, which uses quantum computing. Okay, got it. Got it. Yeah, everything else doesn't. Excuse me. Everything else doesn't. No algorithm has been published that can factor all integers in polynomial time, that is, it can factor b-bit numbers in O of b raised to k for some constant k. Right. Proportional to... So this is logarithmic, right? Basically logarithmic. This is proportional to the number of bits. Polynomially proportional to the number of bits. There have been sub-exponential algorithms which are not polynomial in the number of bits, but sub-exponential in the number of bits. I think that's what that means. And then finally there's Shor's algorithm, which is polynomial in the number of bits, it's b cubed, but it's a quantum computing algorithm, which is not the easiest thing in the world to build. I think the issue with quantum computing is that someone explained to me that it's actually not that it's not doable, it's that it's so much energy is required that it's like basically impossible to scale it to any reasonable use case, which is kind of ironic. It's something to do with energy, and it's just weird, like the physics of actually operating quantum computers is just like impossible. It's a very odd thing. Anyway, alright, let me end the stream here. Just go ahead and do that. So thank you guys for watching. Let's go to the next problem, prime numbers. Alright. Implement Shor's algorithm. No. First X number of prime numbers. Okay, no, that's not too bad. We can do the sieve of Eratosthenes for this one. Let's implement that in Clojure, see what that's like. But I'm not gonna do that right now. I'm gonna end stream now. I'm way over time, and then I don't know what I'm gonna do next. Probably I don't know. I don't know. I don't know what I'm gonna do next. I'll probably come back in a bit because we have a few more hours of time before bed and before work tomorrow. Yeah, it was cool seeing Gilbert Strang show up, right? Because that was one of the guys I learned linear algebra from 8 years ago. How many years ago? Is that right? Yeah, 8 years ago. Yeah, I was like 19 at the time, something like that. And I wanted to prepare for Stony Brook's linear algebra course, so I took his MIT Open Courseware. Is that right? I feel like was it around 8 years ago? Maybe I'm wrong. Maybe it was like 6 years ago or something like that. But man, I remember that. I remember it was really good. That's like, and I watched as many videos as I could, and I spent so much time trying to understand. It's a good time, man. Kind of wish I could go back to those days. Oh man, I don't know. I feel like I was so ignorant of so many things, so many important things when I was younger, and so many things I had to like learn the hard way, like painfully difficult things, having nothing to do with academics, but sort of academic, could have been academic, like just dealing with people, I guess, something like that. I don't know. Reality, I don't know. Anyway, all right. Thank you for watching. I'm gonna end stream here. Might come back for another stream later today, a few minutes or so, and we'll look at prime numbers, implement the sieve of Eratosthenes in Clojure, see what that looks like. So yeah, take care.